So, hello everyone. Welcome to our virtual workshop. Good morning, good afternoon, good night, wherever you are. So we are here today to teach a little bit about Bao, how to give the first steps into this hypervisor and build our version of an hello world as you do when you start learning a programming language, and we want to do the same for hypervisors or for using the Bao hypervisor. This workshop is co-promoted with CROSSCON, and for those of you that don't know, CROSSCON is a European project that aims at providing a software stack that is highly adaptable across a wide range of devices from the low end to the high end, and it aims to provide the security primitives to meet the challenges of the IoT landscape that are envisioned to be very important in the currently and in the future. So next slide. Today's speakers is me, David Cerdeira, and José Martins alongside me. We will be guiding you through this workshop. And we also have Daniel Oliveira and Diogo Costa in the background assisting us. They will be reading some questions throughout the presentation in specific points. And we have here the whole Bao project team. So just to make sure that everyone gets the expectations of this workshop, the main goal is to understand, or the main goals are to understand what are static partitioning hypervisors and what problems they solve, to grasp the Bao architecture and its main features, and in particular, in a more practical sense, we want that you learn how to set up a development environment for a Bao-based system. We wanted to learn how to create Bao VMs and configure some of its parameters, including memory, the amount of memory, or several memory regions, how to give devices to VMs, how to give interrupts. These are the main building blocks for VMs. We also will be teaching you how to establish communication between VMs. And throughout, we will be building Bao-based software stacks from scratch. And in particular, we will be doing this using an emulated environment using IOMMU. Towards the end, we'll also glance over a bit about more advanced features that are outside of the scope of this workshop, including advanced isolation mechanisms and other features. And we'll also talk a bit about current ongoing efforts and future directions for the Bao project. So this is the agenda. First, just a recap and an introduction to Bao hypervisor and virtualization in general in the context of static partitioning hypervisors. Then we'll quickly show the system setup that we will be using. And hopefully, if you guys are trying to follow along to this workshop, you have downloaded the Bao Docker, as that simplifies the setup significantly. Then we'll do 5 examples. We will be building 5 software stacks. The first one, a really simple one, just one guest, and then they will grow in complexity as we move along the workshop. At after each section is presented, we will be giving a few minutes of Q&A, and feel free to ask questions in the chat, and we will read at least a few of them, just to make sure that you guys are understanding everything. After this, we'll show a live demo running on a Raspberry Pi. And then we have the advanced configurations and the conclusion. Just to give you one quick note that all the main sections are building on top of an emulated RISC-V platform. Okay, so now I'll give the word to José Martins, who will talk to you about Bao hypervisor.
Okay, so hello everyone. Now I'll talk a bit about kind of the theoretical, the background concepts of the Bao hypervisor. So we start by framing Bao and the static partitioning, embedded virtualization in general in the context of these mixed criticality systems, which are systems that most often are also cyber physical systems. That is, they kind of interact somehow with the environment and have the main property that they incorporate various subsystems which run at different criticality levels, meaning that a subsystem may be safety or mission critical, and other subsystems may be only a best effort system. They provide some kind of functionality that is not that critical, that essential. So we found this in many industries, so automotive, medical, aerospace, industrial control, throughout the world. And so these mixed criticality systems, by their definition, because they incorporate different kind of subsystems, they have this main requirement of consolidation. They need some kind of mechanism for consolidating these subsystems. And the main reason for this are mainly what they call the swap C, size, weight, power, and cost constraints. So you want to essentially save costs, put these subsystems in the minimum number of SOCs or ECUs, reduce cabling, whatever. So this is the main reason for this kind of systems. And when you do this, you want to do this, of course, with the minimum performance penalty possible. But I would say that the main requirement that we want in these subsystems is that we have to guarantee some safety and real-time properties to the critical subsystems. So you have to guarantee that the non-critical subsystems don't interfere somehow with the safety or real-time properties of the critical subsystems, and of course the critical subsystems won't interfere between themselves. On top of this, security, because it's kind of the other face of the coin of safety. So without security, you won't have safety. So you have to have some kind of security guarantees, some security features here. And finally, certification, because these systems, for them to be deployed, they have to be most often than not certified by some authority. And certification is a very wide topic, but I would say that the starting point for certification is that you have a small code base, a small trusted computing base that is kind of easily inspectable. So this leads us to virtualization. So what is virtualization? Virtualization, very simply put, is a technology that allows us to run multiple isolated and autonomous software stacks on top of the same hardware platform. And so by definition, it gives us this consolidation that we need for the say mixed criticality system. So by definition, it's kind of an obvious solution because it all gives you, by definition, it fulfills this requirement, and also has nice properties such as it provides already a nice fault encapsulation, because this virtual machine abstraction that the hypervisor provides to the virtual machines gives this sense that they have they are the owners of the single hardware. And when one of the VMs somehow crashes, it won't affect the other VM. So already gives you some safety and security properties as well. And virtualization is a really old technology. I think it dates back to the 50s, but in the last couple of decades, it's been more and more adopted, first in the cloud server domain, and now more and more in the embedded world. So the question here becomes, does virtualization fulfills all the requirements of the mixed criticality systems? So, and for this, we'll take a brief look at an hypervisor spectrum. So we start with the traditional hypervisors that were originally developed for this cloud environment. And these hypervisors, they are mainly characterized by having a really rich feature set, which means that they have this large code base and they don't really address the real-time and safety requirements that we need. And these hypervisors will be something like KVM, the original Xen, and these typically depend on large general purpose operating systems, so Linux mainly. So these are kind of out for our requirement. So next we find embedded hypervisors that were already written for embedded systems and have a smaller total computing base, have better real-time properties, but they are really just support this so-called soft real-time. They don't really try to provide really tight real-time guarantees. Next, we find microkernel hypervisor. Microkernel hypervisors, if you are familiar with the architecture, they are kind of secure by design. They follow this really modular architecture, and then the trusted computing base, they push most of the functionality to user space, and the trusted computing base is just this small microkernel that runs in the privilege mode, which is just really good for safety and for certification. But I kind of argue that because microkernels are written, they are very general. You can put both mixed criticality systems and other kind of general purpose systems on top of them. This generality comes at a cost, and this cost is having some issues with the real time and performance, because because you have everything in user space, there are a lot of context switches going on. So on the far side of the spectrum, we finally found these static partitioning hypervisors, which Bao is one instance of. And these hypervisors are written from scratch to target specifically the mixed criticality use case, and provide a really strong isolation and real-time guarantees. So they are able to do this with a really small trusted computing base that's in principle easily verifiable. So besides Bao, you'll find that the Bao was not the first, of course. There were Jailhouse, Quest5, and now Xen provides this DOM zeroless. I think they now call it another thing, Hyperlaunch, I think. Anyway, it allows you to configure Xen essentially as a static partitioning hypervisor. You kind of reduce the code base a lot, and then you have you put aside the Linux DOM 0, and you kind of have a static partitioning minimal Xen system. So static partitioning virtualization, I already laid out the kind of the goals, the principles, but what does this mean in practice? Essentially, it means that there's no sharing. All resources are statically allocated and assigned either at build or at initialization time, and there's kind of no more high-level abstractions besides what you really need to run and modify the guests. So you will have a one-to-one virtual to physical CPU assignment. So there's no sharing of CPUs. There's no scheduling. You just run one guest CPU in one physical CPU. So no dynamic memory allocation. So everything is allocated and mapped at startup time. And then there's no more allocation, no more mapping, nothing more. All devices are passed through. So we assign the real physical devices directly to the guest. The hypervisor does no emulation. It doesn't provide no virtual devices or nothing of that kind, which means that save an exception or two, the hardwares that the guests, the interrupts that the guests see are really the physical hardware interrupts. So, and nowadays, to achieve this with this minimal trusted computing base to fulfill all these real-time and safety requirements, these hypervisors really depend on hardware virtualization support. So that's not there. The architecture, in my opinion, doesn't have that much value. So Bao hypervisor. Bao hypervisor is static partitioning hypervisor. So we support both MMU and recently we had a support for the MPU-based systems, which are basically ARM Cortex-R, but in the future there will be more. We'll talk about it in the end of the presentation. So besides those static partitioning features, those base defining feature of the architecture, we provide also the inter-VM communication, as all other hypervisors do. And we kind of distinguish ourselves because we don't really rely on any other kind of operating system. So Bao is really self-sufficient component. Besides the need to have some firmware to start up the system, Bao is really a standalone component. Which is not the case, for example, for Jailhouse. So we initially built Bao as an alternative to Jailhouse exactly because of this. So we do depend on the hardware system, the virtualization. So we need the second stage translation. And what does this mean? This means that besides the typical virtual to physical memory translation that you find in common operating systems, there's a second stage of translation. So guys will translate virtual to physical addresses, but from the Bao's the hypervisor's point of view, this is a guest physical address, which is for Bao a virtual address in reality, and you will translate it through another page table. So in fact, the hypervisor is in full control of the memory. And so yeah, so we also use the interrupt virtualization support present on the interrupt controllers. And this is important. It also depends on IOMMU. So because all devices are passed through to the guests, these devices might have some kind of DMA capability, and we need to isolate them. Otherwise, all bets are off. The guests can do whatever they want. So we need an IOMMU. It's essential for isolating these devices. So some other interesting points that we did when we wrote Bao at the beginning. So there's a internal isolation in Bao. So kind of a CPU that's mapping a VM wouldn't see another VM's memory, or for that fact, the other VM's managing structures in the hypervisor. So you kind of isolate the hypervisor internally. We have support for we kind of focus on as much as possible using super pages, which, as we'll see, simply removes performance degradation a lot. And we also have this mechanism called cache coloring that allows us to partition shared caches so that we avoid interference between guests. And finally, Bao has we believe, very permissive license, Apache v2, and the code is, as you all know, open on GitHub. So a couple numbers about Bao. So Bao is around 8,000 lines of code. It depends a bit on the architecture, on the features that we enable, but that's about it. Sometimes 9, sometimes 7 for RISC-V, for example. So Bao, in the bottom graph, you'll see that Bao has, if you turn on if you can configure Bao using super pages, which is not, it doesn't happen all of the time unless you are really aware of what you're doing. But if you get to that point, you have essentially 0 overhead when running a guest. But if you're running a guest with the normal 4K pages, you'll get overheads of about 5%. Here we see also the effects on the top graph, effects of cache coloring. So we have the green bar shows the same benchmark when it's under stress from other guests that are continuously reading and writing memory. And we see that from that 0 overhead, we can go up to 100% overhead. And if we apply coloring, we can mitigate that to about to almost about half. So it's not perfect, but it's a help. And finally, we see that we have somewhat low IRQ latency. So an issue with this hypervisor is that the current hardware doesn't allow us to inject interrupts directly on the guest. So the hypervisor has to receive the interrupts first and then re-inject it on the guest, which adds to the guest latency. But we are able to, on the ARM platforms, to keep this sub-microseconds. So the bare metal latency would be about 290 nanoseconds, and we get it to about 900 nanoseconds. And so we also see that interference, if you have the same kind of interference we have in the previous graph, if we do this, it also affects the interrupt latency, but with coloring, we can really mitigate it. So all these kind of numbers, and if you are interested in knowing more about kind of the concepts and the features of static partitioning hypervisors in general, not only Bao, we published this paper last year that has a lot of information on this. So to finish this part, I think we talk a little bit what Bao supports. So Bao was originally developed for the ARM v8 A64-bit ARch architecture, but now we have support also for the 32-bit version. We also support the ARM v8R, which is the MPU version of this architecture. And we also support RISC-V. Right now, we only support RISC-V 64-bit, but I think Bruno is working on porting it to 32 bits, and we'll also add support for using the various MPUs that you'll find on the RISC-V architecture. So we'll support a lot of vendors, and for RISC-V, we support the FPGA cores that you are able to run on FPGAs from the Open Hardware group, for example. And so, as I said before, to run Bao, you really need some kind of firmware for most of platforms, which mean in ARM, the ARM trusted firmware, in RISC-V, the OpenSPI. And we, throughout the last couple of years, we run a lot of guests. We have some bare metal guests. General purpose operating systems, we mainly have run Linux, but we have run different Linux flavors, also Android, the Ubuntu, and a panoply of RTOSs, so Zephyr, FreeRTOS, Notex, Erica, and I think maybe a couple more. So recently, I think this was as announced, we added the Bao awareness to the Lauterbach tools. So soon, if you have the Lauterbach tools, you will be able to debug the Bao more easily. So at this point, we'll have a short Q&A. No, I think we don't have time. Don't we have questions in the chat? No questions right now? Okay, so we'll skip this and we'll start going into the tutorial, the workshop itself. So first, a little bit about the system setup. We will be using this Bao Hello World repository that one of our colleagues, Diogo, wrote, and will be basing the workshop in it. So you can, after the workshop, go there and follow it by yourself. So don't feel pressure to put in all the commands that we'll be putting in. If you want to just watch, you can watch and then do it later. So we already, for starters, we should clone this repository. I think we already did this, right? And yeah, and we are already there. Okay, so a little bit about the components that you need to build if you want to build a software Bao-based software stack. Let's put it that way. So besides, of course, Bao itself and the Bao configurations, you of course will need to build the guests that you want to run over Bao, and you'll need to, as I said before, build the firmware components. So in this case, because in this tutorial, we will be targeting the IOMMU RISC-V Vert platform, this firmware will be OpenSPI. So now we prepared a Docker container that has all the tools that we need to run this tutorial. So first of all, I want to apologize because yesterday some people come to us because this only supports the x86 architecture. So we didn't prepare an image for the now widespread, I think, ARM-based platforms. So we'll do this, I hope, in the next few days. So it will give you the image and you can use it to go through the tutorial on your own time. So I will start by opening the container. And so first of all, we will set up a few environment variables. First, the cross compile that indicates us what is the cross compiler we'll be using throughout the tutorial, which is the RISC-V bare metal toolchain. And then we set up a few environment variables that so that we can kind of organize where we put each source, the binary files, etc. We'll be using these variables, these environment variables throughout the tutorial to place the various components. So we've done this. Now we build a couple of directories that we'll need from the get-go. And at this point, we should have this this directory tree that has all the files that we will need to go through the tutorial. So, okay, let's go for the first part of the tutorial. So we'll do a very simple Bao configuration where we'll have a single guest with a single vCPU. So with a single vCPU, 64 meg of memory, and we assign it a newer device. So let's go a bit through the configuration. When you start configuring a Bao system, you will need a .c file that has this struct config structure. So Bao will assume that you will pass it this file when you will build it. And this This structure has two main variables, let's say. The first is a VM list, which is an array of, maybe I can go to the code. Yeah, so if we go to the, so you have the VM list, which is an array. Let me go here. Here. So a VM list, these are the main points that we need to configure. A VM list, which is an array of structures which are a VM configuration in the VM list size. So right now we have only one VM, so VM list size 1, and we configure this VM config struct. So we'll start by configuring the image. So we have a couple of macros to configure this image correctly. And what you need is first declare the image using this VM image macro outside of the struct, and give it an identifier, a variable name, and then put a path. This is essentially a path. We use some macros too, but a path to where we will place the final binary of the compiled guest. So then when in the VM struct, in this image field, you will use this macro VM image built-in to tell it, okay, for this VM, I want to use the bare metal image, which is this variable that is the same that's here, and tell it the guest address, the guest physical address where we want Bao to put this image. So this macro is called VM image built-in because what Bao will do is it will incorporate the VM binary in its own binary when it builds itself, and then at runtime it will relocate the guest image to copy the guest image to the right place. So next, we have to add an entry point where we want to Bao to jump in the guest's address space when it starts the guest. So here we just put it on the same base where we put the image, right? Okay, so these are the first 2 points. Next, we have this. So here we went to the image, the entry point. So let's leave these to the CPU affinity and colors for later. And then we have to define the guest platform, the VM platform. The VM platform, we start by defining the number of CPUs we want to assign to this guest. So in this case, as I said before, only one vCPU, so CPU number 1. Next, we need to assign it a number of memory regions. And you have to, for the memory regions, you have to tell it, okay, I want to have one region in this case, just really simple, but you can add as many as you want. And for each region, then you have an array of VM memory regions. For each region, you have to specify the base where you want the guest to see this memory region and its size. So this size is 64 meg in megs, right? And we also have the base to be the same base at the entry. And so we put the image in the base of this region and we jump to the base of this region when we'll start running the guest. So besides the memory regions, we'll skip this IPC, which are the communication configuration that David will talk further ahead in the presentation. We have to configure the devices. So for configuring the devices, it follows the same pattern. We have to tell it how many devices we want to assign to this guest. In this case, 1, only the UART. And then we have an array of VM device regions, which we need to fill in a few fields to configure it. So first, there is this PA, which is the physical address, the real address of the device that we're assigning to this guest. So it's at this address. And then there's a virtual address, which is essentially the guest physical address. So the address where the guest will see this device. In this case, we choose the same, but we could have chosen a different one. Then we put the size of the region that this device requires, so the MMIO region of this device. And a small point here is that this size will always have to be a multiple of the minimum page size of your architecture, which both in ARM and RISC-V is 4K. For the MPU, I think is 64 bytes. So this size has to be a multiple of that size, otherwise the Bao, I think, will emit an error. So then you have to tell Bao which interrupts belong to this device. So this UART has only one interrupt. It has its interrupt number 10 on the Chemo platform. And that's basically it. So to pass through a device, you have to configure these fields. So another small point, there are the one device for each architecture is implicit, which is the interrupt controller, which is a special case because it has to be emulated by Bao. Either way, for this, you have this arch field, which is specific to the architecture that you are targeting. And inside of it, you have a couple fields. In RISC-V, you only have the PLIC, which is the platform level interrupt controller base. So you need to tell Bao where does the guest want to see its interrupt controller. So in this case, this is the 0xC000, which I believe it's actually the same as the physical address, but it doesn't really matter. So now, this was a very simple configuration. So we can go through it. Where is it? It's where, okay, here, yeah. So this is the configuration that we did. So we start by declaring, we have to declare the header that has all these definitions, of course, but then we have to declare the image, tell it where the binary is, say, okay, you want to have one VM. Actually, this is outdated, this configuration, but you can fill in this information by yourself, but the idea is that you really use this macro, and that we only have to give it this bare metal image and then the base address. Then you have the entry points. Also, this is outdated, right? Okay, this one CPU here, right? And okay, so this should be one CPU. I think it's not updated, but okay. Either way, the idea is to have only one CPU here, and then the region that we define here. Okay, the device. Okay, this is an outdated version. Is for the ARM architecture. I think this is the version for the ARM architecture, because this timer interrupt is for the ARM architecture. Okay, but either way, the idea is the same. So this wouldn't be here, and there's one device here, which yeah, it's basically this and the PLIC. Okay, so now we can go to the. I hope this doesn't affect the demo, but yeah, I tried this all yesterday, so I think it's working. So we will start by now. After configuring, setting up the Bao configuration, the next part is configuring the guests, building the guests. So we have this bare metal application that we use mainly to test Bao, and we'll use it for this demo. So we'll first set up an environment variables to where we'll place the code. Then we will clone the code. It's really small code, so it should be. Okay, we already have this. Yeah, so do you want me to
maybe start from scratch?
Start from scratch?
Yeah, just to go over the
okay.
The cloning process really quick.
So sorry guys, we will set up this again from the beginning. Maybe okay. Yeah. Okay, let me just so I'll create a new repository, a new okay. Now let's go back a little bit. Sorry for this, and we'll clone the repository from. Okay. Hope this doesn't take too long. Okay, so now let's go to Well, hello world. And once again, start up the container. Okay, we'll probably need to restart the environment. Okay, build those directories we needed. Okay, now we go to the configuration. And now we'll go build the guests, bare metal guests. So hoping now this works. What? Okay. Okay, so now we have the bare metal guests. Now we'll apply a couple patches that are we change the application for illustration purposes of this demo, and then we just build it. So we have two commands, so the patching command and then the build command. So when you build this application, you just need to tell it which platform you want to build it for. So it's the QEMU RISC-V Vert platform. So okay, we build it. Now these couple commands move the final binary file of the build to a repository where the Bao configuration is expecting it. So yeah, it just copies over the file. And now we'll build Bao. We'll do kind of the same thing. We'll set up a directory for Bao and clone Bao to that directory. Okay, we have the Bao code. Now we'll build Bao, and here I can maybe I'll first build it and go through the build command after. So okay. Yes, we've built Bao, and for building Bao, the command is quite simple. Essentially, you need to pass it only. Let me say, this command is a bit more complicated than required, but I'll try to simplify it. You only need to run make on the Bao top level directory and pass it two parameters. So the platform you want to build Bao on, so in this case, QEMU RISC-V Vert, and also the configuration that you want to use. So in this case, the configuration, as I said before, is just a .c file, and this is the name of the .c file. It's the bare metal configuration we want to use. Now, a small point is that you can also tell Bao where to look for this configuration. So in this case, and for this, you use this config repo option, where we tell it, okay, in our directory structure that we figure out for this demo, we will put the configurations here. If you don't pass it this, by default, Bao will look in the config directory that's next to the code. But in this way, you can have configurations in different folders, organize them, etc. But so to recap, you only really need the platform and the config. These are the essential two parameters you need to build Bao. Tell it what platform, what configuration. So Diogo here is also passing the CPP flag to define this directory, because this is the directory that we use here to tell it where the image is. But this is just to simplify the tutorial, is not really required. So let me go back. Okay. No, okay, now once again we copy over the Bao final binary to a place where the QEMU will be expecting to the file. And before we run it, we still need, as I said before, so guests, configuration, guests, hypervisor, firmware. For RISC-V, we use the OpenSPI firmware, and we'll first clone it. Okay. Now we will build OpenSPI using this command. How will we build it? We use this firmware payload option, which allows us to embed the Bao's binary directly inside OpenSPI's binary, kind of the same way you embed the guest's binary inside Bao. and we tell it here, okay, we want to use the payload, and the payload path is the Bao binary. So essentially, we build OpenSBI in this way. I think there are other ways to do it that doesn't require this, but this is the simpler way to do this, in my opinion. So we'll just build it. Okay, just taking a bit longer. Yeah, okay, nice. And once again, we always copy the final images to a final directory so we know where they are. But yeah, so this was to build this simple guest. This was basically it. Once again, configuration, guest image, Bao image, firmware. So now we will run the this configuration on QEMU system RISC-V 64. And basically this platform is a 4 gig platform with 4 CPUs, which is what Bao is expecting. And we pass it so as a BIOS, this OpenSBI object file that we just compiled. And also, so there's a bit of noise here. These options are the options for enabling some devices that we won't use right now, but when we run the final demo using Linux, we'll assign Linux these devices. So right now you can ignore this. This part is the essential part. So I'll run it and hope it works. Okay, so now we have OpenSBI booted. You see here Bao booting. Bao just prints some small stuff. Some people say it's too hidden, but yeah, it just prints a message. So I'm here, and there's also this issue that the RISC-V right now, at least Bao doesn't support the cache management operations in RISC-V. So until we add this functionality, you always see this warning message because Bao is expecting to flush some caches at this point, and it doesn't have the instructions to do so. So it emits a warning. But for QEMU, this doesn't really matter. So, okay, this is basically it. The first demo is this really simple thing that, so as you see, the bare metal guest had only one CPU and was kind of receiving one timer interrupt at each second, I think, and printing out a message. So now, I don't know if we have some questions.
So we have a first question here. It's from Azam. The question is, how can we add an extra OS in Bao? For example, how can a Zephyr VM be integrated in a Bao setup? What are the required changes?
Okay, so that answer sorry. So that answer will be answered during the tutorial. So this was the first small example. So we will be our idea with this tutorial was to add little changes to illustrate exactly this kind of point. So today we won't be using Zephyr, but we'll be using FreeRTOS as an example. But then you can go to the Bao demos repository. We'll also be talking about it, and there you have configuration specifically for Zephyr. And if you have some kind of other target platform, you can talk with us. So.
Another question is, how does Bao guarantee real-time in contrary to other hypervisors that offer soft real-time, like Xdriver?
So the way not only Bao, but the static partitioning architecture kind of gives some really good real-time guarantees. The main reason is that it doesn't do any sharing. So no sharing of the CPUs, which I believe Xvisor does. No sharing of the CPUs and no scheduling. So the CPUs you assign to the guests are always there for them, which really gives you a good starting point for real time. The second point I would say is the philosophy of building these hypervisors to have them really kind of feature stripped, doesn't have many functionality, so you will always have kind of really hopefully deterministic and fast paths, for example, for interrupt control, for interrupt injection and that kind of thing. So I believe the architecture itself gives you these real-time guarantees. Then there are other stuff you can add on top, but I believe the basis is this idea.
And I have another question. It's from Pranesh. Maybe we should ask you to clarify it, but I will throw it either way. How are the real-time APIs from Bao exposed to applications?
So Bao doesn't really have APIs, or for that matter, real-time API. So the abstraction that Bao presents to its guests, to the virtual machine, is that of a real machine as much as possible. So there aren't really APIs. So the only API we have now for Bao, and I think David will talk about it, it's an hypercall so that you can communicate with the other guests. But if you are running a standalone guest, what the guests see is called, in virtualization terms, the full virtualization, right? It's like as much as possible the real machine. So there are no APIs. In these architectures, the real time comes from the way you build the hypervisor and the fact that you do no sharing. So that's why, of course, this has the other side of being inefficient, right? So if you are assigning one core to one guest, and because you want the core to always be there for that guest, so it can really have real good real time, if that core remains unused most of the time, is inefficient. But so choosing these hypervisors is kind of a trade-off in that way. So I think that would be my answer. I hope I clarified. So Daniel is telling me that right now we don't have more time for questions. That'd be other slots for questions, and at the end of the presentation we also will open the floor to more questions. So right now we'll keep going. So before adding other VMs, we will kind of show you how would you change these VMs. So I need more memory, I need more CPUs. So this was the configuration we had before. And now we will not have only one CPU, not have 64 meg, but actually we will give all the vCPUs to the VM, and it will increase the memory. So what are the steps that you need to achieve this kind of modification? It's kind of obvious, but we want to illustrate it, right? So the first point here is that, okay, we didn't really need to, but we modify the guest code so that, okay, this guest, it knows that we modify this mem size in the application. It knows that it has more memory, but it won't actually use it. It's just for illustration purposes. And we reflect this change that we changed in the guest in the configuration. So the configuration previously had this 64 meg. We changed the size of the configuration, right? So this is what you need to increase the guest's memory. And then essentially, very simple, the same thing for the number of CPUs. We had one CPU, now we have 4. Just a small point here is that, and this, we really want to improve the error feedback of Bao. This is one of our targets in the next times. But if you actually add more CPUs to a guest, or to the total number of guests that are available in the actual physical platform, Bao won't emit an error. So Bao will just stall somewhere when it's configuring the virtual machine, and not give you any feedback. So be careful. If you increase the number of CPUs, you really need to make sure that there's enough CPUs for everybody. So now we will just basically rebuild Bao. So there's actually there's a small mistake here, because technically we would need to rebuild the guest application because we changed it. But as I said, this is mainly for illustration. So, and if we recompile it wouldn't really use that extra memory. So we use the same guest binary, and we just rebuild Bao with the new configuration. So in this application, let me just, yep. I'll go. Essentially, now we will just repeat all the steps that we did before for the same. So we copy the binary file. We rebuild OpenSPI. So as I said before, OpenSPI embeds Bao binary, so we need to rebuild it so it embeds the new one, and then copy the SPI file to another place, and finally run QEMU. So my point was that now you see that the application is running the 4 CPUs. Each CPU is handling its own timer interrupt. And my point was that this application kind of detects at runtime how many CPUs we assign them. So we didn't need to rebuild it so that this modification took effect. So I think, yeah, this was really simple. So we have another small Q&A right now. I don't know if there are any questions.
So we have a question and a follow-up for that question, maybe from another person, but I'll give them the two of them. How Bao handles updates over the air? And this following question is, does it have to update all guests, or we can update them individually?
So Bao right now doesn't have a feature for updating guests as you would expect from a general purpose OS or some similar system. So right now, if you are trying to update the guests, the workloads that are running atop Bao, what you have to do is similar to what you do with firmware. So you just have to flash it on an SD card, on the embedded memory, and yeah, that's pretty much it.
Maybe, but there will be people working on that too.
Regarding that feature, so this is the state right now, but regarding that feature on the updates, we are working on it in the context of the CROSSCON, as we have a few requirements regarding the firmware update, and yeah, we are still studying the exact features that are relevant for the most part, or for the devices. If we want to have one VM update at a time, we're still evaluating the trade-offs, but yeah, that's something that's definitely on our mind.
Yeah, let me just add that if you have interest in that feature, because we will be working on it. If you had some feedback on the requirements that you need, then can describe to us your use case. I think that would be very helpful to us. So please drop us a line, send us a message, and we'll be very grateful. So, okay, there's no more questions. I think I still have one more stretch to go before the vid comes in. So now, addressing that question a while ago, how do we add another guest? We'll go through that now. So now what we'll have is a dual guest Bao configuration, which keeps there the FreeRTOS guest, the bare metal guest, and adds a new FreeRTOS guest. For this, so this is essentially the configuration. So we previously gave the 4 vCPUs to the bare metal guest, but now, of course, as I said, you'll need at least one CPU for FreeRTOS. Actually, FreeRTOS only uses one CPU, so we give one vCPU to the FreeRTOS. And also, we also give the same UART to the FreeRTOS guest. And this is an important point. Maybe I'll stress it when I go through the configuration. So once again, what do we need to do? Okay, we first need to declare the FreeRTOS image, as I've done before. It's the same idea. And then we'll need, of course, increase the VM list size. Now we have 2 guests, so 2. And we use declare the image, as we did before. We say we want to have a built-in image for FreeRTOS, this FreeRTOS image, and we'll place it at address 0. So FreeRTOS will start from 0. Okay, these are we took it out for the space, but of course we still maintain there the original bare metal guest configuration. So this is not 2-entry array now. And of course we we change the number of CPUs we had previously for the bare metal guys from 4 to 3, and we set 1 CPU for FreeRTOS. Okay, that's pretty much it. So we could go through also the memory and the devices, but it's essentially the same. Actually, the device is actually the same, and now maybe I can go through that point. Is that while Bao really manages memory, so Bao won't allow you unless you explicitly say so. For example, for the communication to share memory. For devices, this is not the case. So if you assign the same device to 2 different guests, Bao won't complain. Bao will just let you do it. And this is the way we are actually sharing the UART here. And this is something I believe we are not completely happy with. We are doing things that will allow you to check it if this problem exists in your configuration. But a small point here is that it allows you to share the MMIO, the IO region of the guest. It won't allow you to share interrupts, because the way interrupts are managed by the hypervisor, it really isn't possible. So you shouldn't, let me just say, you shouldn't do it if for some kind of debugging demonstration purposes you want to share a UART device, for example. It's what we are doing now, okay, but we'll probably in the future obviously forbid you, lack of a better word, to do that.
Maybe go over the full configuration.
Okay, but now I have to change. Can you change the code?
Let me see if I can open the correct folder. Oh, half day. Oh, hello world. You should have this on the complete folder.
So yeah. So now I hope to have the correct configuration this time. So we have the bare metal FreeRTOS configuration, and just to go through it, you have the 2 image declared here. We have the struct config struct. This I didn't know if I mentioned, but this is kind of a legacy thing. We don't really need it, this configuration header. And actually in this configuration, we don't need this too, because there's no communication. But okay, we have 2 VMs, a VM list size of 2, and here we have the bare metal configuration, and here we have the FreeRTOS configuration. So the bare metal configuration you already saw. So the image, the entry point, the number of CPUs, regions of memory, the devices, and the interrupt controller. And exactly the same thing goes for FreeRTOS, right? The memory region is at a different address, so this we actually don't need. This you actually don't need. So the devices, so you are giving, as you see, the same UART. The physical address is the same, but this time, for example, FreeRTOS wants, the way we built FreeRTOS, it is the UART at a different address. So it's the same UART at a different address. And as I said before, you can't actually share the interrupt. So the interrupt is only assigned to the bare metal, not to the FreeRTOS. But yeah, this is pretty much it. Let me, how do I, the Z, first one was there.
Oh.
Okay, let me just, okay.
Should be,
Yeah, let me just.
make sure it's in the file.
Okay. Sorry for these incongruences. But okay, now let's do it. It's back, right? Target share memory.
Mm-hmm.
Yeah. So let's get back to building our guest. So it will be a bit repetitive once again, but yeah, we set up the directive for FreeRTOS. We clone FreeRTOS. So this is a repository we manage where essentially the bare metal runtime used by FreeRTOS is the same used by the bare metal application. So with just the FreeRTOS functionality on top. But yeah, we will build it. Okay. Okay. Now it's cloned. So now we will build it. Just not really that relevant, but just to explain this, we apply a few patches as for the bare metal application, so that it really matches what we want to say, and we pass it this parameter is a standard address space, so that the way we build this environment, we have a way so that for every platform you have different addresses, but if you want to have the same, always the same address space layout, you can have this standard address space, and these applications will always use the same addresses, so that simplifies when we want to test the same thing in multiple boards without really changing the configuration. So yeah, but simply when you build this FreeRTOS version, you just need to once again pass it which platform you want to build. Okay, so now let's run this command and build FreeRTOS. So the bare metal, guys, I think we will then copy the binary over, and I think we won't. Okay, we copy also the bare metal. So, and I'm not sure, Diogo, why we need this, but okay, I'll do it anyway.
Put it in a convenient place on the directories.
Okay, but to make a point, we're just shuffling files around, so at this point it's not really critical, but okay, we will now build Bao, and we change the configuration to be this bare metal FreeRTOS configuration, so which is this .c file that I was showing you a couple of minutes ago. So okay, hopefully this will build correctly. And once again, we copy Bao, then we will go to the OpenSPI. Yeah, these are always the same steps. We just wanted to add this step by step so you can follow it without any mistakes. And now we will run IOMMU, and hopefully, yeah, now we have the two guests running, sharing the same UART. So there was some crash here in the UART, so because they are not synchronized, but yeah, 3 CPUs for the bare metal. FreeRTOS is running 1 CPU with 2 tasks. And yeah, this is basically it. I think this part is over. Yeah, I don't know if we have more questions here.
So we have a first question from Play. Is there any plan to generate a guide for porting Bao to a new board and a new SoC ARM-based, for example?
Yeah, we will make this point at the end of the presentation, but more than features, now we are really trying to invest in infrastructure, and part of that is documentation. And documentation, we are attacking actually four things. First, the user manual, which is something like what we are showing you right now. So how to configure Bao, how to use Bao from like a pure user standard view. Then troubleshooting, so what to do when Bao doesn't work. An internals guide, so if you want to develop in Bao, we want to add documentation to help you go through the code itself. And fourth, a porting guide. So that's definitely on our agenda, and I think you'll see it in the next couple months.
And another question from Hazan: does the two virtual machines need to have the same UART?
No, actually, that's a good question, because that's a point I didn't make. We are only using the same UART here because IOMMU is kind of limited in that way. It only gives you one of these UARTs, and the other way you can print in IOMMU using virtIO, but these applications don't have drivers for virtIO, so we are just sharing it for purely practical reasons. So as I said, you actually shouldn't do it, right? And we'll probably add something that doesn't allow you to do it in the future. So right now you can do it, but you shouldn't really do it. This is just for demonstration purposes. So okay, there's no more questions. I think
It's
It's-
coffee break.
oh yeah, it's a coffee break now, a 5-minute pause, and then David will come in and go through a couple more configurations with some other features using Linux and communications between the guests. So yeah, see you in a few minutes. I think 5 minutes, right? Yeah, in about 5 minutes. So see you soon.
Okay, guys, we are now resuming again the workshop. I'll hand over to David that will present the Linux part and the shared memory with its multiple VMs.
So I think you can hear me. Let me just make sure everyone have okay. So let's get right into it. Or rather, I realized that in the introduction I didn't really explain how the Bao project was related to the CROSSCON, although you may have figured it out already. In CROSSCON, we are leveraging Bao to establish multiple isolated environments. We are actually exploring Bao to build TEs, and naturally this requires a little bit more flexibility than that is provided by static partitioning hypervisors. So yeah, just wanted to give you that context that why is the CROSSCON project interested in Bao? And sorry, I missed that in the intro. Okay, but now let's go right into our next examples here. Now we have built simple systems. We have built two systems with two VMs, and as is the case for these types of systems, and as Martin was telling you about in the introduction, it's really a key point in these types of systems that we are able to integrate critical and non-critical systems or subsystems in these devices. And so naturally, some of you are interested in running Linux or other general purpose systems. There isn't really much for a need on a specific OS integration apart for the IPC, which I'll be talking about further on. But yeah, we are establishing Linux as a VM, and we will run Linux alongside the bare metal VM. So for the bare metal VM, we are giving it one vCPU, 64 megs of memory, and one UART, same or very similar to what we've done previously. And for the VM2, we will have a Linux-based operating system. This is a really simple Linux build. It does not feature a storage device, so it's the rootfs is loaded. RAMFS, yeah, so it's loaded in memory. So a very simple device. Of course, you can have more complex systems, and as we've led on in earlier, we have managed to run Bao underneath Android and other complex OSs. So Linux will be running as a guest, 3 vCPUs, 1 GB of memory, 1 console, and 1 network. And these devices are provided by QEMU. And so they are virtual devices. They have a bit of nuance to them, but the core thing is that these 2 devices are given to Linux. So for the configuration, very similar to the FreeRTOS example, we now need to include the Linux binary in the config file, and we are doing this magic with macros to get the Linux binary. And I'll go a bit into what this Linux binary actually is, but let's just focus that it's a payload that includes Linux. We have to have 2 VMs, VM structures, so we have the VM list size 2, and we are including we are using the macro to signal where the image is loaded on the config file, or yeah, the VM. So very similar as before. On the bare metal side, we are removing the 4 vCPUs that we had at some point, and now we're giving it only 1. And for the Linux configuration, we are giving it 3 CPUs. I would really like to stress that it's of utmost importance that the Linux device tree, I don't know how familiar you are with this, but the device tree details the platform that Linux is running on. This is a mechanism for ARM and RISC-V. Intel-based systems is a different kind of hardware, figure out where the hardware is. But it's very important that the device tree matches that configuration file, otherwise you will have problems. So in this case, just very simply, we are establishing through the device tree that Linux has 3 CPUs, and of course this matches the config file. And after I'm done explaining these key points, I will show you the 2 files side by side. So the second point is the memory that we are now giving to Linux. The base address is 9000 and the size is 1 gig. And of course, as I was saying, this must match the device tree. And here we are using the memory node at the base address 9000 with the size 4000. For the devices, and as I've said earlier, we have a console and a network device. We are actually giving a full MMIO memory range. So now that this may seem a little bit weird because previously we have 1 device and 1 MMIO region, but the way we are doing this right now, Bao has this flexibility to establish full MMIO memory ranges. So this may be more convenient if you are giving a large amount of devices to your VM. And in this case, we are having, we are giving the Linux a large MMIO address space, which starts at 10001000, and with this size. So actually we are giving more devices than the Linux will need. And we are giving the corresponding interrupts. So this corresponds to 8 devices, and we are giving 8 interrupts, 1 through 8. So to stress this point again, it is of utmost importance that the device tree matches the config file, or the other way around, the way you want to look at it. But in the device tree, we have to have the devices that we are giving Linux. So we are only giving 2 devices. So the first ones are the ones that matter. And we have these 2 devices here. One will be the console and one will be the UART. And finally, as Martins has explained before, we must give the interrupt controller in RISC-V its PLIC, and this must match the device tree configuration. And the key point here is the address, and yeah, we have the same configuration on either side. So now let me just quickly go over to the config file, just to make sure that we have a full picture. I'll open this full size. Hopefully I don't mess anything up. And if I'm not mistaken, the device tree is right here. Kimo RISC-V, Linux. Let me see if I can do the split screen. Okay, I think it should be visible. So yeah, for the bare metal application, we have the same as before. So I don't think there's really a need to go over it. Let me just collapse this. We have the Linux image using the macros. And now let's try to look at it side by side. So 3 CPU numbers. We have the device tree establishing the CPUs for the platform. So we have 3, 0, 1, 2. Then we have the memory region. And actually here we are doing something that Martin...
Yeah, let me just make a point. I will talk about these 2 options in a few slides, but the important point here is that these devices that we are assigning Linux on IOMMU have DMA capabilities, and we don't have an IOMMU in this platform to control these devices specifically. So Linux, here we essentially are identity mapping Linux so that Linux is the same memory addresses as these devices. So yeah, that's why you have this configuration here, but I will detail how it works in a few slides.
Okay, Martins. And so we have the memory region starting from 9000 with 1 GB size. We have the memory node here. We have the device and MIO region. And again, although we are only establishing 1 region, we are actually allowing for 8 devices on these types of devices, virt and MIO. So no need to go too much into detail on this one. And then we have the PLIC, the interrupt controller that we establish here. So, and again, one last time, the device tree should match the config file. They should be defining the same platform. So now let me go back to this. So typically building Linux takes quite a bit of time. So we have pre-compiled it, and it's available in this Bao Hello World repository. So just to get things moving, let's create a directory and copy the pre-built image into it. And now we'll copy the bare metal image, same as we've done before. Now that we've put the images in places that the configuration expects, we will build the hypervisor and make sure that you see the config file, that you set the correct config file. Okay, now let's copy the output to a convenient location so that the Open SPI can see it and include it, and it's built. Okay, now let's put it on a place where Kimo can find it. Lost my mouse for a bit here. Okay.
You should make a point about the downloader.
I'll make it in a little bit. So now let's the part that Martins was telling you about that is unnecessary for the earlier examples is now needed to go to this example. So we are creating or we are configuring QEMU so that it creates 2 virtual devices, 1 net device, and one UART. Okay, so this is what this command is doing. Let's run. Let's set up the platform. Okay, so now we have the bare metal running on the physical ward, if as you might think of it. But Linux is running on the virtIO ward. So let's see how we can connect to it. If you look at the output of QEMU, oh, so this keeps scrolling. Okay, let me see if I can show you. Okay, I can do a better way. Okay, so let me just hold the execution. So when we run QEMU, QEMU will output the device where it will output the virtMMIO ward. So we'll just take note of this. Now let's continue. And I will need to set up a second terminal because this terminal is occupied. So we have open a second terminal here. Oops, not this one. This one later. Okay, let me do something differently. Open tab. Okay, this is gonna be easier. And because we are doing Docker, I will attach to the running Docker. So the way we do this, and we actually have this explained on the next slide. So Docker PS to see the list of running Dockers, and we will connect to the one that we are interested in, and we will run the bash program. So we made a note that it was the PTS1. So now I'll just use my preferred terminal. This is just a few options to handle special characters, and then I will open the PTS1. And now I can interface with Linux. So yeah, anything you can program, I can try it. Okay, so yeah, so now we have a full Linux system running here, and yeah, it's running alongside the bare metal as it handles the interrupts. Okay. Oh, so this left out. Let me just scroll. Okay, so now I'll give word to Daniel to read some questions if there are any.
Okay, we have two questions again from Azam. Thanks for the active participation, Azam. Does it matter how to build rootfs, build root, buildbags, etc.?
It doesn't matter how you build it. The key point here is that on a typical Linux-based system, Linux will have access to storage. So if you know a little bit about the way Linux typically boots, Linux is booted with a RAMFS, a file system that is loaded into memory with Linux, and he will use this for setting up, finding devices, etc. And then it will use rootfs on the storage, the built-in storage on the platform. So the point here that I made is that this particular Linux instance is running fully off of memory. And in a case where you want to use a more typical scenario for a build root where you install the rootfs on the SD card, for example, you actually have to use the Bao configuration to give that hardware to the Linux VM.
So let me just make a point. This kind of thing, so what exactly is running the VM? Bao doesn't really know it's Linux or is anything else. So the kind of, if you use build root, Yocto, or whatever, it doesn't really matter. It doesn't really matter also if it's a RAMFS or not, because if you assign it some kind of block device to the guest, it can use that block device. So for Bao, this kind of thing doesn't really matter.
Yeah, so hopefully that answered your question.
The second question for the Azam is there a DTX for FreeRTOS as well?
Maybe Martins can answer this better.
Yeah, so the really simple answer is no. So FreeRTOS, at least the versions I know of, don't use a device tree. So you kind of configure the in code using macros, what kind of memory and CPUs it will use, that kind of stuff. And yeah, but for example, if you use another FreeRTOS Zephyr, it will have a device tree, and you'll have to follow a similar kind of manual modification of the device tree as we just illustrated it with Linux. So the process will be pretty much the same.
Yeah. So now let's go into the next example. And the next example is establishing inter-VM communication. So this will be our last example and our most complex one so far. So yeah. As before, we have the same hardware platform, but now we are configuring it with what in Bao we refer to as the inter-partition communication, an IPC. So same as before, 1 vCPU on the bare metal, 3 vCPUs on the Linux, 1 GB of memory Linux, etc. So the way we do this, in the configuration structure, we must declare a shared memory region, or a shared memory entry. And the one particular detail is that the index on this array will be the ID of the shared memory that we will be referencing on the VM configuration file. So this shared memory is not, this structure in particular is not specific to the VMs. So now we must, in each VM, we must create an IPC object or an IPC struct. Starting for Linux, we will present the shared memory at address F000 with this size, which I believe is 0.5 meg. And the shared memory ID, as I was telling before, is 0. And we are actually, the IPC mechanism is based on interrupts as well as shared memory. So we are giving one interrupt, in this case is interrupt 52. And again, as I made the point hopefully clear before, we have to pair the configuration with the device tree, and we are creating a device tree node for the Bao IPC. And one note regarding this is only possible because we have a device driver that implements this communication. So just to go quickly over this Bao IPC node, we have a shared memory region, which starts at F000, and it has the same size as before, in the configuration, I mean. And the way this driver works is you establish a read channel from which Linux will read, and the write channel for which Linux will write, and we give it the interrupt 52. And finally, we assign it the ID of the shared memory, the same as the config file. Okay. So now, before going to the bare metal, how do we incorporate these modifications with Linux? Let me just establish the environment real quick. Stop QEMU, and do this. Okay, so in this step, we have a device tree that I can show you, but we have a device tree here that includes the Bao IPC. And the format that Linux is expecting is a device tree binary, device tree blob. I'm not exactly sure at the moment, but we will use the device tree compiler to compile the DTS to device tree blob. So let's do this, because this is the first step. And now we will use a piece of glue code, which we call the Linux loader, L-loader. And this is a really simple code that will just incorporate the device tree blob and the Linux image. And it will run just a little bit of assembly so that the device tree, the boot process, the Linux boot process is met. So in this case, Linux is expecting the device tree address in the first register. And this is what this glue code is actually doing. So it's very simple. We just run the makefile on loader and establish the architecture we are running, the image of the Linux executable, and the device tree blob. So we provide these paths, and then we'll provide an output file. And we have our Linux binary that the Bao configuration can now include. So now to go over to the bare metal application, we are actually giving presenting the shared memory at the same address, F000, but remember that these are virtual addresses. So it could be a different address depending on your application with the same size, the same shared memory, and we are giving it one interrupt once again. Okay, so now let's apply a patch that allows the bare metal application to actually handle the communication from the shared memory. Okay, now let's build it. Okay, everything went fine. And now let's copy it into a place where Bao can find it. Let's use Bao to incorporate these two config files. Once again, keep note that the config file is not changed from the previous one. Okay, so a note here regarding the config file. Now we will copy the Bao binary into a place where the firmware can find it, SBI. We will compile SBI, and we will copy its output to a place where QEMU can find it. And finally, we are going to launch our virtual platform. So the FTS1, we are running a bare metal application, same as before. I'm just gonna run the same command. Just clear this. Okay. So now, if I do this, I can see that I have a node in the device folder, virtual file system directory in Linux. And if I actually write to it, I can see okay, that the bare metal application correctly received the message.
Let me just make a point about the mechanism that's happening here.
Yeah, sure. You can
So
go over it.
essentially, what's happening here is that when we wrote a small Linux driver, that when we write to that device, Linux will write that message in the shared memory and invoke a Bao hypercall. This is the API. Right now, is the single API that exists in Bao. Is that the guest invokes an hypercall so that Bao injects an interrupt on the other side. So what will happen? Bao will receive the hypercall, will inject an interrupt in the other guest. That guest, the bare metal guest, receives an interrupt and will print the message as a response. So this is the basic mechanism. So at this point, there is some code in the guests that are aware of Bao for the communication and have specific APIs for these hypercalls.
Yeah, so I'm just trying to show you on the code side here that this is a patch that includes the driver in Linux, and just want to
actually we are using the RISC-V one.
Oh, yeah, okay, yeah. And we have a firmware call that uses the shared memory information, IPC information, and this will trigger an interrupt, as Martin was saying. Let me just try to quickly go over to the patched code. Okay, yeah. So in the main, body of the application, we actually install the handler for this interrupt, and upon an interrupt, the handler will execute, and it will just read the message for the shared memory. So, yeah. Now a few questions.
So we have a first question from Johannes. I hope that I'm spelling your name correctly. As soon as you halt the execution of Bao, what happens to the files that are stored in the VMs?
So with our setup, and I assume that this is what you are asking, in our setup, the files are, how to say,
volatile.
They are volatile, so they will lose all the modifications you made while the Linux VM is running is completely lost, because the file system is
it's RAM file system.
It's a RAMFS file system that is loaded at boot time, and that does not change with the execution of Linux.
So if you do want to have these changes to the file system persistent, you would have to assign some kind of block device, an SD card, whatever, to that guest. You can do it, you can pass it through, and use that device as a file system. So we mainly use the RAMFS file system for demonstrations and for our academic research when you use Linux, but on a real system, you would need to have this non-volatile file system for sure. And I can just make another point is that we are working on virtIO support that will enable you to share a single block device for multiple guests. And we'll talk a little bit about that later. Any more questions?
No.
Okay, two more questions for Azam again. The IPC node is not listed as a device. What are the implications of declaring shared memory node in devices? It won't be cacheable?
I think it's a good question. I don't think I fully get it, but I would say that, so I will make the distinction because in the Bao configuration devices, you are passing through devices, right? That's a real device configuration. You are saying this real device, I wanted to pass it through to the VM. The IPC thing is, although I think you get the point that we model it as a kind of device. That's our goal, but it's not really a device, right? It's two things. It's the shared memory, which is only mapping a shared memory, and it's the interrupt. So the guest gains access to some hypercall that allows it to inject interrupt in the other side. I don't know if I full get your point. What was the second part of the question?
The second part of the question is, for the IPC node, there is no physical and virtual address. Does that mean the base is mapped?
I think I get your point, because you are making a comparison between IPC and the memory regions, and Bao will allocate. Actually, I'm not 100% sure if you can specify a physical memory region as shared memory, but Bao will allocate, will identify a piece of memory that is not being used, and will use that memory region as shared as they are needed.
So maybe now I get it. So when you specify the shared memory, you don't need to specify an address, because Bao, as with most of the memory regions we've been detailing until now, Bao will allocate that when at initialization time it will allocate it. So you don't need to specify it, but I will show in a few slides that if you want, you can do it. If you want to say, I want this shared memory to be in the specific region, you can do it. I will show again in a few slides.
Okay, so time is running short. I'll try to be very quick. I will go over one live demo, but just before, I want to let you know that we have a repository. This one you are hopefully seeing, the Bao demos. And here you have a very easy way to try out Bao. One key point: do not try, at least we don't recommend that you use this repository as your bootstrap environment. This is really developed just to be kind of run one command and make everything run all at once. So not really ideal for iteration and modifications, etc. So if you are interested in Bao and you want to try a few other examples, let me just quickly go over into this table, which maps all the platforms that we are currently supporting on this repository with the various configurations. Okay, so now let's go to the Raspberry Pi live demo, and hopefully everything will work. Okay. So if I'll just do some quick demonstration. Okay, I have my commands here. So this is just to set up the environment, the cross compile, the demo that we are building, and the platform that we will be building for. And after this, we can just run make. And I'm not going to go through this, of course, but this will just clone everything that you need. And at the end of this step, you will mostly have a running system. You just need to perform some SD card setup that I've already done. Yeah, so this is really easy to use. So now for the demo, I'll just connect the Raspberry Pi I booted earlier. So let me just reset it just so I can interrupt the boot flow. Okay. Let me just run this uboot command that will find the Bao bin that we have set up earlier. And this is now running the, actually Zephyr OS, so not FreeRTOS. Sorry about the mishap. And I'll just connect to the Linux OS through the network, because we are not actually giving a wart to Linux, but we are giving it the Ethernet. So yeah, now we are inside the Raspberry Pi. Let me just try to show it to you that we actually have the setup here, and we are clearly not faking it. Yeah, so it was really simple. I can show you the IPC as well. Or yeah, so moving it around, yeah, moving it around, rebooted it, but yeah, you can trust me that the IPC works. We've shown before. So let's move on with more interesting topics.
I think you can go through the. Yeah, can you? I think you can go fit with, right? No.
I think it's automatic.
Fits with.
Okay,
it's okay. It's nice.
Okay.
That's right. Okay, thank you, David. So we're almost at the end. So I think more 10-15 minutes will be done. So now I'll go through a list of kind of we considered advanced Bao configuration. So what you've seen until now, it's really the base of what you need if you want to run something, but you can tweak it around. We have a few more options, and I'll start with this that I think we mentioned throughout the presentation more than one time: static allocation. So in these VM regions, you have two more options that allow you to specify what is the physical address that you want this let's say virtual region to be. So if you don't specify these two options, the place physical and then the physical address, Bao will allocate it somewhere, and is not, if you are using an MMU system, is not actually guaranteed that it's contiguous. So Bao will allocate pages as fast as possible, to be true, and doesn't give any guarantees where they are. So if you want to do this, there are various reasons for it. One of them is the one I told before about don't having an IOMMU, so the CPU has to see the same thing as the devices. That's one possible reason. There are many others, but what you really need to do is just say, place this region in a specific physical address. So this place phys option is as true, and then give it the physical address. So this both forces the base address and a contiguous mapping. So on this base, on this physical base, this region will have this size contiguously. This is guaranteed if you do that option. And so, as I said, this is a straightforward way to have identity mappings. And a point here is that, okay, Bao really does check this. If you do this and you have the same addresses for different regions, Bao will check this. Bao, it will emit an error saying you are trying to allocate something that was already allocation. So these static allocations work like this. And the small point is that some people try to use this for on-chip memories, for SRAMs, but what we really recommend for these SRAMs is that you model it as devices. You pass it through as devices. Second point is that when you are configuring a device, in the really good platforms, you will have an IOMMU. I think most of them have it, but that Bao supports, but some don't. And you will have to, if your device is a DMA device, you will have to add this ID, which is the bus master ID of this device on the platform, which can be either kind of hard-coded in the hardware and you will find it on the SoC technical reference manual, or sometimes it is programmable. And for the platforms that it is, what we do is we have a fork of, so this IOMMUs only exist in ARM platforms, so there's no RISC-V platform, real platform supporting hypervisors right now. For the ARM platforms, in the ARM trusted firmware, we have a fork that allows you to fill in a table saying which devices will be assigned to each ID, so you can do that. You need to kind of do that manually before building the firmware. And there's a couple more options specifically to the ARM SMMU. You can tweak things around just to show you that there are more options on this way. You can optimize the way you are using the SMMU, the IOMMU resources. So third point is that, okay, recently we've been really focused on MPU-based systems instead of MMU-based systems, which means we don't have virtual memory. And so how does this reflect on how you configure Bao if you want to use a Cortex-R? So the main thing is that when you are configuring these regions, the memory regions, these two fields are implied. So you don't need to actually say place fees true and fees at the same address as the virtual base, but Bao assumes for these platforms, Bao assumes this will be true. It will check it, but it kind of assumes this is in the configuration. So you have to do this. Another point is that for devices, if you remember, you have the physical address and the virtual address for devices. On these platforms, the virtual address is just ignored. So if you place another virtual address, Bao will just use the physical address. And another point is that although you can use the macro that we've used until now, the VM image built in the guest images on Bao, these on the MPU systems, for reasons I don't really have time to explain right now, but drop me a line if you want to get into it. You shouldn't do that because this will waste memory, because you don't have the flexibility of mapping things around with the MMU. So what you really should do is just have the bootloader place the guest image in some known place, and then this macro tells Bao, okay, I have preload the image, so we don't really need those macros that declare the image binary, but I've preloaded the image at this address and the image has this size. So you have to do this manually. You can use the other, but you'll have some inefficiencies. And also you can configure Bao to be relocated to a given address, because this is a physical address. Bao itself also won't have flexibility of virtual mapping. So if you want to move Bao around according to your manual static memory allocation, you can relocate Bao to some specific address. So yeah, another small point, another small no, but a feature that we had in Bao from the beginning is cache coloring. So for MMU systems, we allow you to partition the last level shared cache so that you can have some kind of avoid conflict misses between the VMs. So there's no interference at the level cache between the VMs. As I showed you the graph in the beginning of the presentation, this has significant advantages, and also has some disadvantages, because this causes memory fragmentation. It makes you use small pages, which, as I showed before, also adds performance overheads. And you can do this in the hypervisor. You can color the hypervisor itself. In the configuration, you have a NIP structure, which you are allowed to put the colors in. So the colors field is a bitmap. It's kind of, I won't go into details, but in most platforms, you will have around 18, 16 colors. And this field is a bitmap of the colors, and you put a 1 in the colors that you want to assign to the hypervisor. The same thing goes for the guests. So in this example, small example, you are actually, if you have a platform with 8 colors, we are assigning half of the colors to the hypervisor, half of the colors to the guest, which means half of the last level cache to the hypervisor, half to the guest. But typically, you would want to do this between guests, not between the guest and the hypervisor. And a small point, someone raised this issue here, is that you can also do this for shared memory, and I don't think I mentioned it. These place fields are also valid for shared memory. So not for the VM memory regions, but when you declare the shared memory object that David showed you before, the list of objects, you can say, no, I want the shared memory to be at this specific place. So you can use this with the shared memories too. And finally, a couple other, I don't know if you have much time. These are really small issues, but I would highlight this feature here where you can set the CPU affinity. Basically, when you are configuring a VM, you have this field that allows you to tell about which physical CPUs you want to put these VM's CPUs in. So again, this is a bitmap. So this is 5101, which means that I want to put, imagining this VM has 2 CPUs, I want to put the CPU in vCPU 0 and in vCPU 2. So it allows you to control this. And okay, we'll just finish the presentation. So for some, at the end, we'll have time for a couple of questions more, but we are already on the top of the hour, so I'll try to be quick. So main takeaway point from today, first of all, thank you so much for being here, for taking these 2 hours, a lot of time for going through this with us. So we went through what virtualization, very briefly, what embedded virtualization and static partitioning is. We learned how to configure VM, the VM resources, how to add different VMs, how to change the parameters, how to configure the VM communication, and also Linux, which is more complex because you have to manually go through the device tree. How to build all these components, that we did this ad nauseum, right? And we went through a demonstration of Bao on the real platform, which is the Raspberry Pi, which we believe is really a widespread available platform. That's why we focus on it. And also we went through some kind of advanced Bao configurations. So last slides, what are we planning to do next? So first of all, as I said before, we are focusing on kind of not on the features themselves, but on kind of infrastructure and support. So we are working on documentation, and we will first focus on the user manual, which Diogo has been working on. And you see here, I think we will publish it somewhere in the next month. So you finally will have some kind of documentation for checking, for using Bao. All the things that we said today will be on this part of the documentation. Then we'll have a troubleshooting guide, a porting guide, and an internals guide if you want to contribute to Bao. Next, we've been working on CI infrastructure, so mostly on 2 things: adding checks for code quality, so static analysis checks. We just started this adding the checks recently, but we have many more on the pipeline, and we also been building a testing infrastructure. We'll start adding tests to Bao really soon, mainly for regression testing. And feature-wise, what do we have in view? First of all, we'll be adding some sharing features. So a lot of feedback we've been having in the last couple of years is that, okay, static partitioning is good, but the trade-off is really strict. So no absolute sharing. We want to be able to share it, to share things, CPUs and devices mainly, on a configuration basis. So virtIO support, device sharing. We've been working on this. João has been working on this, and we'll probably be releasing a virtIO demo in the next month or so. With right now you are using IOMMU as a backend, but we are working on have standalone backends using Rust backends from the Rust VMM project. Also CPU sharing. So we'll be adding some kind of mechanism for sharing CPUs between VMs. but we are really still looking at how we can do this efficiently and without breaking the properties that we want if you still want to keep Bao as a pure static partitioning. So we are studying it. We have prototypes. We are looking at the best way to do this because we don't really want to break what we have, want to add and not really break what we have now. So next, architecture support wise, we are focusing on MPU architecture. So RISC-V has a lot of different MPUs. We'll be targeting that. Also, we've been working, we've been studying, but we'll start working on it soon. A port for the Infineon Aurix TC4 cores, which have virtualization dual stage MPU support also. Third, we want to work on the user experience. So mainly we are working on this, and we'll be giving you configuration tools that will kind of guide you through the configuration, perform checks on the configuration, and do things like automatically DTB generation for Linux guys, which is a really cumbersome and error-prone task that you have to go through if you want to run Linux on these systems. And finally, actually something I didn't put here, but it was mentioned, update support. We also want to work on that. That's something on our pipeline too. And just to end, so we want to add MISRA compliance to the best of our abilities. We've started looking at this. We've been taking ideas from what the Zen project guys are doing on refactoring Zen to MISRA. We'll be following their ideas, and we haven't started with this because we want to first have the testing in place so that the MISRA code modifications we can test for regressions. And finally, Diogo has been working on the bandwidth regulation, so event-based bandwidth regulation, and it's done, but I think it will be public really soon, but we won't merge it because we still have a lot of questions on what is the best way to use it. But it's another microarchitectural isolation mechanism that we will for sure head in Bao. So finally, thank you a lot for your time. Please send us your feedback. GitHub is our first choice for feedback. So issues, PRs, discussions, whatever. If you have some more private inquiry, you can email us at this email, info.project.org. And okay, we are on these 3 social networks: Twitter or X, GitHub, and LinkedIn. Please follow us there. And once again, thank you so much for coming today. For those of you who want to stay, we have time for questions. So yeah.
Okay, let's go for some quick questions. So a question from Gian. Is DMA available to VMs? If so, how to manage the fact that they are not aware of the underlying physical address that may differ from their intermediate physical address?
So Martins can talk about this. I can mention through the presentation.
So as I said in the initial slides about static partitioning and about Bao, so we do rely on some kind of IOMMU. We need it so we can do the pass-through of these DMA devices. Without it, all bets are off. So you're completely right. The main issue here is that so I would say about 40% of the platforms with support 30-40 don't have an IOMMU, but they do have, most of them, if they don't have an IOMMU, they have some kind of MPU. If you have an MPU, and what we are planning on doing, we are planning on supporting these MPUs. We plan on starting, it's not right now, but because we don't have the resources, but we plan on adding drivers for MPUs for the various vendors. The problem is
very vendor specific. Yeah,
it's very vendor specific. So there will be a lot of drivers. If it was just only one, like the IOMMU, we would already have written it. But we do plan to use it. And then if you do that, you can use the mechanisms that we talked about, static allocations, maybe with the configuration tools that I was telling about before, you can kind of automate this process, but you kind of force the guests to have a physical identity mapping. So if they are using a DMA, that requires an MPU. So yeah, I think that's the state of it. Thank you for the question.
So a follow-up question for Gian actually is, I guess Bao relies on level 2 MPU for Cortex-R52, isn't it? So do you plan to port Bao to Cortex-M that only support level 1 MPU?
There have been discussions. I think there have been discussions, but the main conclusion we came up with is that, okay, Bao needs to have the specific hardware support. If you start to get kind of exotic and hacky and have many tricks, for example, Daniel is the expert on Cortex-M here, but I know that Cortex-M isn't actually like classical virtualizable, fully trapped and emulated. So if you wanted to port there, you need to have some kind of binary patching of privileged instructions. So it would be very messy. So we've talked about it, didn't put it completely aside, but I think it's not on our scope for the next few. Yeah.
And maybe just to expand a bit on your question, if you're trying to get a Cortex-M processor on a Bao-based system, it would be probably better to think of it as a device. So as a standalone island that Bao can actually isolate using the available mechanisms, and not itself as one platform that is managed by Bao inside, if I'm making myself clear.
Yeah, for sure. So I think just a little bit that if you are talking about those Cortex-M CPUs that you find on platforms that have the full-blown Cortex-A cores, yeah, we've done that. We kind of assign that those cores are typically go through the IOMMU or the MPU, and we've done this. We've assigned them to a VM, but as a device. But if you are talking about boards just with Cortex-M, for now, that's out of the scope.
Okay, another questions for Hazem regarding if you want to reach out. That's why I asked David to go back a little bit of the previous slide. So we have here all of our social media. Please try to use the GitHub. Is our first choice to reach out. So please use it. And regarding your question, Hazem, if is Zephyr on Raspberry Pi demo available on GitHub? Yes, it's available on GitHub. It's out on the repository Bao demos, as David is showing now on the screen sharing. And we have a lot of examples for a lot of platforms. I will leave the link on the chat so you can follow it and try it by yourself.
Yeah, and I want to thank, I think Yan, I don't really know how to pronounce the name, Yan G, I think, that he actually contributed with that demo, so really recently. So if you are here, thank you.
So another question is from Clay regarding CPU sharing. Will this push Bao away from static partition hypervisors? What are the use cases?
Okay, so that's our kind of our internal conflict, right? Yeah, it would definitely, if you add that, it would stop being a pure static partitioning hypervisor. I think there are use cases for it for sure, because as I said, we took this decision based on feedback from some people that play around with Bao, use Bao in some context. I don't know the specific use cases, but there are people that looked at Bao and said, okay, I like it, but I need the CPU sharing. But it would definitely get it away from the pure philosophy of the static partitioning. That was the whole Bao thing. So we are taking time with it, but because we want that, okay, if you use Bao as a static partitioning, you get the same thing you get now. if you want to enable the CPU sharing, okay, you lose something only in the cores that you share. So I think there's a challenge. So how do we modify the code base to add these features so that we don't break some of the code paths that are really minimal, that give Bao the properties that make it a static partitioning and hypervisor. So this is the challenge here for us, I think, and this is why we are taking our time with it.
So, and another question from Johannes: can you name some examples of IoT devices which could potentially take advantage of Bao?
So one that comes to mind, and I'm not an expert on IoT applications of any sort. Usually we dabble on we focus on the devices themselves and not really too much on the applications. But one device that comes to mind that seems to be really interesting from our point of view is the BeagleBone AI 64, because it has, I believe, neural processing. So it has, I think, Cortex-M processors also in there, auxiliary processors. It has quite powerful cores. So this is a really interesting device, and although it may be a bit more on the expensive side, it's not so much that it's unaffordable. But I think pairing BeagleBone AI 64 is really interesting. Also drones and robots. We are also looking into this in the CROSSCON project as well. Sorry. So in general, really powerful platforms that feature lots of resources and things that really can be isolated from each other, I think, are the main targets.
Thank you.
Hopefully that answered.
Okay, and regarding Leonardo, if we are sharing the recording of the workshop, yes, we are sharing it. I cannot stress enough. Please follow our social media. The GitHub has a lot of stars to be done, so please do it. And we'll be sharing the workshop recording on the following days on our social media.
Thank you everyone for coming.
Thank you very much, guys.
And thank you for the questions. It was really interesting to share this with you. So see you next time.
Yeah, I hope to see you soon. All. Bye.
See you guys.